So I want to introduce Aayush. So Aayush, I think a lot of people know the Modeling Toolkit project at this point. As we're entering to V10. Um, it's been a long project that's been going on with SciML, but within the last year or so, Aayush has really been actually the main contributor. If you check out the contributor graph, it's been his project. So here, Aayush is going to be the one to talk about what's going on with Modeling Toolkit V10 and all the new stuff that's going on and also the future of it. So take it away, Aayush.
Thank you. Yeah. So hi everyone, I'm Aayush and I'll be talking about what's new with Modeling Toolkit. And just as a preface, I'd like to say that I'm going to assume that people here have a working knowledge of Modeling Toolkit. But if you don't, just feel free to listen in and let me know if you have any questions. So before we get started, just a quick introduction about me. I currently work at Julia Hub and I maintain most of the open source symbolic numeric infrastructure that we rely on. So that's Modeling Toolkit, Symbolics, some amount of symbolic utils, and the surrounding packages. That's my GitHub ID, and I am active on the community Julia Slack in the SciML related channels. So if you ever want to reach out, you can reach out to me there. So the first thing I'd like to get started with is a feature retrospective of what we've built over the past around 1.5 years. And there's a lot of stuff to cover here, so buckle your seatbelts. First up is MTK parameters. This is one of the defining changes for Modeling Toolkit version 9. And what it really lets us do is have type-stable heterogeneous parameters. So we can have different parameters of different types. They don't even have to be numbers. So in this example, you can see that I have a parameter f there. It's a function that takes a real value and returns a real value. And it's any arbitrary function. I can use it in my code. So I can call it as f of t or f of x or f of 2x plus y plus z, or really whatever expression. And I can just create my ODE problem, and in my ODE problem, I'm going to say that f is a sign. And I'm just going to solve it like any other ODE problem, and if I plot the solution, I get the time series out. And the really cool thing about this is you can just swap out the functions. So as in this slide, I can just swap out f for cosine, and it effectively just works. It just solves with cosine now. And this sort of swapping can also work during runtime. If you do it, for example, in a callback that just swaps out f for another function, which is pretty cool. Another thing that the parameter struct lets us do is parameter optimization. So we can solve for parameters against some experimental data. And so I have a really trivial system here, and it has 4 parameters, alpha, beta, gamma, and delta. And so you can see alpha, beta, and gamma are normal, and I've marked delta with this tag called tunable equal to false. So what this means is that I want to solve for alpha, beta, and gamma because they are just by default tunable, and I don't want to solve for delta. And so I'm just going to show the loss function really quick. And the loss function is pretty simple. All we're doing is we're taking the ODE problem. And this is the really critical line where I'm just, in using the SciML structures API, I'm going to say that I want to replace the tunable part of my parameters with x, where x is the optimization state. So the values of alpha, beta, and gamma that the optimizer is currently working with. And so I just swap those in with my parameter object. I put that into my ODE problem, get a new ODE problem with the updated parameter object, and then I can just solve it and calculate the loss against my data and return that. And so using this loss function, we can set up the optimization function and the optimization problem and give it like a random 3 values as the starting point, and give it the lower and upper bounds and all of these standard optimization.jl sort of workflows. And once I solve my system, so I can just do the same thing again. I can just take the solution and replace the tunal part of my parameter object with the optimized values from the solution, and voila, we have an ODE problem that we can just symbolically access and get the updated values of alpha, beta, and gamma from. And so this is something really cool that we've been able to make really easy with the SciML structures workflow and its integration with MTK parameters. Next up is initialization. So this has been one of the major continuing themes throughout Modeling Toolkit version 9. It took a while to get right. There's a lot of moving pieces and a lot of user-facing workflows that we wanted to make as intuitive as possible. So what initialization really does is it solves for the initial conditions of your system. So it's an ODE, a nonlinear system, so on and so forth. And so I've taken the classic pendulum example, and it's set up in a way that y and y prime are the differential variables, and we have the 3 other algebraic variables and correspondingly the algebraic equations. Now, traditionally, what you'd have to do is you'd have to specify the initial values for the differential variables. So you'd have to specify y and y prime here. But the thing is that this choice is really arbitrary, and Modeling Toolkit can change at any point in time, and you might change your model, and you might end up with a slightly different state selection, and then have to give a different set of initial conditions. And initialization just kind of makes that really easy. So in this example, you can see I'm going to provide an initial condition for x. So I'm going to say that x is 1 at the initial time, and the derivative of y is 0 with respect to time. And so like x is not really a differential variable here. It's an algebraic variable. But Modeling Toolkit is smart enough to figure out that I have 2 initial conditions, and I need 2 initial conditions, and I can solve for the rest. And as a user, you don't really have to do anything. You just give the initial conditions, you create the ODE problem, and we'll solve it, and it just works, which is really neat. One thing it lets us also do is ensure that your initial conditions are consistent. So for example, in here, I'm going to use a bad initial condition. I'm going to say that x and y are both 1, which of course is impossible because the string has a length of 1. So you can't really make it have a length greater than that. And the first thing that this will do is it'll tell you that the initialization system is overdetermined. So, and it's because we we only need 2 initial conditions. You've given 3. And so Modeling Toolkit is going to tell you that you probably have something is probably going wrong here. And if we still like persist and try and solve it, well, it's just gonna not solve. It's gonna say that there's an initial failure, which means it couldn't initialize the ODE, which is exactly what you wanted to tell you, because you don't have a consistent initial condition, maybe because there's some default in your really large hierarchical model that you forgot about. Next up is polynomialization and homotopy continuation. So just as a primer, homotopy continuation is an algorithm for solving systems of polynomials and obtaining all of the roots of the system of polynomials, which is a reasonably common workflow. And so we have a SciML interface to that through nonlinear solve HomotopyContinuation.jl, and it just allows you to create a nonlinear problem and solve it with homotopy continuation as long as it is polynomial. Modeling Toolkit can generate code for this interface, and it can do a lot of really cool extra things. So like this is the system of polynomials that I'm trying to solve here, and I think you'll notice that the first one is actually a rational function. And in the denominator of the rational function, we have x minus 0.25. So while x equal to 0.25 is a root of the second polynomial, it's not a solution of our system because it's going to make the denominator of the first one 0. And if I just create the problem and use the HomotopyContinuation.jl algorithm and I solve it, so in the solution, you're going to notice that the first element in both of the vectors is not 0.25, because Modeling Toolkit got all of the roots, and it was smart enough to figure out that, hey, I can't use 0.25 here, and it just ruled those out. Now we can also leverage symbolic solvers in symbolics.jl to make this even cooler. What we can do is we can recognize that some systems are not polynomial by themselves, but are polynomial in some non-polynomial terms. So here I have the exact same system, except instead of x and y, I'm using a and b, where a and b are some weird non-polynomial functions. And because we have symbolic solvers, we know how to invert these symbolic functions, and I can just solve my system and get all of the roots of x and y, because I just solve for a and b, and then I use the symbolic solver to invert the mapping and get the values for x and y. I have double the number of roots because there's 2 solutions for x for every given a. And I'd really like to thank Yasin and Alexander. They worked on the symbolic solvers in symbolics.jl, and they're really, really cool. So go check that out. Next up is FMU components. So this is Modeling Toolkit's interface to FMI.jl and FMUs. We can import FMUs in Modeling Toolkit and just use them as Modeling Toolkit components or as entire models. We support both version 2 and version 3 of the spec, and we support model exchange and co-simulation FMUs. We don't yet support the entirety of the spec, but we have a decent bit of coverage, and this is still a work in progress. So we're going to evolve this and add more features as we go along. So like, for example, this is a system of a spring pendulum from the FMI zoo. And if we just import it as a component, we can have the symbolic variables mass s and mass v. There's a little bit of name mangling going on, but that's, as I said, it's a work in progress. And so we can just solve it like any other Modeling Toolkit system, and we get out the time series solution. Another really cool thing that we've added recently is dynamic optimization. So we can solve optimal control and related sort of problems. So in this example, it's an ODE, but we have a cost and a constraint associated with it. So we want to say that the value of v at t equal to 1 it should be 0, and that we want to minimize the value of maximize the value of x at t equal to 1. And so we can just provide those to the system, and we can simplify it, and we can say that these variables are inputs to the OD, and this allows us to code gen to a variety of optimal control solvers. So we integrate with PyOmo, with Casadi, with Jump, with InfiniteOpt, and with boundary value DFQ.jl. So it's just you just create a jump problem or an InfiniteOpt problem, and it just works effectively. And there's more. There's going to be more about this at a talk later in JuliaCon Local Paris. So go check that out. Now, this is probably my favorite change. This was introduced in Modeling Toolkit version 10, and it's the new unified sort of system type. So up until version 9, we had like a really wide variety of system types, and so we had OD system that generates to OD problem and DD problem as a summary. We have a lot more. But so like this diagram really maps out like what systems kind of generated what sorts of problems. But if we really take a close look at it from the perspective of OD system, let's say. If you have an OD system and you add noise to it, you get an SD system. If you have an OD system, you add jumps to it, you get a jump system. If you have an OD system and you just forget about the independent variable for a second, structurally what you have is a nonlinear system because you can't take derivatives and things like that anymore. You're solving for fx equal to 0. And so discrete systems and hybrid and OD systems are essentially the same thing. Like the discretes are just discrete time instead of continuous time. And if you combine them, you get what are known as hybrid systems, where you have some continuous time and some discrete time dynamics. And so it makes decent sense to just have them in one. Implicit discrete system is just the DAE analog for discrete systems, where you have some algebraic equations that require a nonlinear solver. And optimization system, as I demonstrated earlier, if you combine those with ODs, you get what is known as dynamic optimization. We can also just solve them on their own. And so this is why we kind of combined all of this and we ended up with just one system type. And the idea is an LLVM-esque architecture, I'd like to say, where you give us everything as true. So like any sort of new symbolic problem, you just tell us what's true about your model, and you create a system, and then we can generate a variety of, we can generate an OD or an SD or a variety of optimal control solvers, and so on and so forth. And no mention of this system type would be complete without this quote from Chris in one of the pull requests, where we're really just talking about an optimal discrete continuous differential algebraic stochastic jump delay equations. And so I'm not even going to try and figure out what that acronym is, but I think if we get together, we can probably add a few more letters in there. So that's a project that I'd like help on. Another thing to cover is implicit discrete problem and improved symbolic callbacks. So as I mentioned earlier, implicit discrete is the DAE analog for discrete systems. Here I have the traditional Fibonacci sequence in X, and the second equation is saying that the EXP of Y is equal to X. I'm going to pretend that I don't know how to take the natural logarithm of this equation. So I can just create my implicit discrete problem, and I solve it, and from the solution I'm going to ask for X and the residual of the second equation, and as you can see, we get the Fibonacci sequence as the first element, and the residual is almost 0 throughout, which is exactly what we want. Now, why does this matter? This matters because we can do some really cool things with symbolic callbacks here. So I'm going to go back to our good old friend, the pendulum system. And what I'm going to change here is that I'm going to add an event where every 2 seconds, I'm going to say that the value of X after the callback is going to be some function of the value of X before the callback. So with V10, we're going to say that before the callback, the value of a variable is denoted with pre of that variable, and the value after is just the variable. And what this lets us do is just have a completely declarative semantics for what callbacks do. And it allows Modeling Toolkit to be able to figure out consistent state for the system after the callback. So if you're going to notice here, for example, that we're changing X, but X is an algebraic variable. And if you try and do this with ordinary DFQ, if you just have a callback that modifies X, well, ordinary DFQ is going to go, well, my algebraic variables are not satisfied anymore. X squared plus y squared is not 1. So I'm going to run brown full basic init. I'm going to make my algebraic condition satisfied again, and it's just going to solve for X, and it's going to reset X back down to the manifold, which is going to make it like the callback never happened, and it's just not what you want. So Modeling Toolkit just handles that for you. It ensures that the system is consistent and that ordinary figure doesn't do any funny things. And if I just create and solve the OD problem, so you can see that every time X sort of jumps up or jumps down, Y also correspondingly jumps up and jumps down to make sure that the system is satisfied and we still have all of those callbacks working as intended. Next up is common sub-expression elimination. So this is uses the hash consing work that Bowen talked about earlier, where now we're just by default generating really optimal functions for every single function that Modeling Toolkit generates. So here I'm just going to take a very trivial example where we have x squared plus sin x squared times t, and so x squared appears twice in the expression, but you can see that here we only compute it once, and we just kind of multiply it with t, and then reuse the same as a result from earlier to avoid having to compute x squared twice. And this applies to any sub-expression that's repeated in your equations. These are some honorary mentions. We've had like almost 100 releases since Modeling Toolkit version 9 came out, and there is no way that I can cover everything that that we've had going on. But there's this, and there is more. So yeah. There's also some infrastructural level changes that I'd really like to go over. So not everything is code. There's a lot more to maintaining open source software. One thing that we've worked on really is improving the maintainability of our code. So we have, of course, the unified system type makes it just a lot easier. But for example, we've reorganized our workflow so that anytime you construct a problem, whether it's an OD problem or a nonlinear problem or a boundary value problem, we're going to go through that process simul problem function. And so it ensures that every time we construct a U0 and a parameter object, we're doing it the exact same way. And if we find a bug, we fix it for every single problem at once. And in a similar vein, all of the generated code goes through build function wrapper. It's an internal function. Please don't try and use it. But it ensures that any optimization that we do to our generated code is just applicable everywhere across every single function that Modeling Toolkit generates. There's also been a bunch of work around CI and testing to make sure that Modeling Toolkit is continues to be robust and reliable. Every pull request, every bug fix adds a test. We run tests against Julia LTS, latest stable release of Julia, and the latest pre-release of Julia to make sure that we're forward compatible and we know about bugs and newer releases when they as soon as possible. We also now test against release versions of downstream packages as opposed to just against the master branch of those packages. This is currently only set up for Catalyst, but of course we're open to doing it for more packages as we go along. We also test against more upstream functionality, so places in packages like ordinary DFQ or SIML sensitivity where they use Modeling Toolkit in their tests, well, we run those tests from Modeling Toolkit to ensure that we don't break those. And a new addition is the benchmark CI, so we run a few benchmarks to ensure, like, for example, OD problem compile times don't just go through the roof because, spoiler alert, they did a while ago. There's also been some improvements to documentation. So we have much better internal documentation. A lot of our internal functions, especially the newer ones, have doc strings. We have all of the utility functions have doc strings. We document all of the keyword arguments. And we have a new developer documentation section in the docs. So anybody looking to contribute just knows a little bit more about how things work internally. We also have a new API documentation section with Modeling Toolkit version 10, and the goal here is that every single public API function has a doc string that documents both the public and the non-public API of that function, and we leverage Julia's extended help functionality to sort of hide the inner details from the user in the REPL. And the API docs just list out all of this. In fact, we've run into issues with Documenter trying to erroring out because our pages are too large. Just to wrap up the presentation, I'm going to talk about what's next for Modeling Toolkit, what our goals are for the future. Of course, in continuing in the vein of documentation, we want to rework our doc pages. We actually have a discussion ongoing about this. So the goal is to rewrite it for a newer version of Documenter because the original docs are written for a very old version of Documenter that doesn't have all of the nice things that it has now. There's a new structure that we're going for where there are tutorials that really hold your hand through common workflows and tell you explain like every little bit of what's going on, as well as a separate section for examples, which are just really just snippets of code that show what's possible with Modeling Toolkit and sort of common user workflows that people might encounter and the best ways to do them. And of course, the aforementioned API documentation and developer documentation that we're always working on expanding. There's also been significant effort that's been going into and will continue to go into improving scaling. So one of the first things on that list is support for array expressions and array equations. Anybody who's used arrays enough in Modeling Toolkit has probably run into that warning. That's a very annoying warning. And like as a summary, we're just trying to support make it go away and really support arrays as first-class citizens in Modeling Toolkit and throughout a symbolic-numeric stack. This ties into the next goal, which is to integrate with Reactant.jl, which will allow us to generate really performant array code and target a variety of architectures with it. So to be able to deploy and solve our systems on like GPUs and stuff. There's also an ongoing rewrite for the core of symbolic-utils.jl for improved type stability and performance, as well as to make arrays first-class citizens, as I expressed earlier. So just huge free speed up for everyone without really knowing what's going on behind the scenes. That's always nice. We're also looking into like really specialized code generation pipelines. So for example, one thing that's going on right now is semi-linear ODE problem, where if you have a differential system that's expressible as sort of a linear transformation of your state plus some nonlinear term, so ax plus some c function of x, we can typically this happens in PDEs. Where your discretized PDE has a really big linear part that tends to be stiff, and the nonlinear part tends to be sparse and non-stiff. And so we can split that out, and we can generate a split ODE problem and target our implicit-explicit split solvers, and just get a huge speed up without you as a user having to do much other than add 4 letters or however many letters to the beginning of your ODE problem. There's also a bunch of just other new features that we're that we're working on adding. The first one is analytical integration. So for several trivially integrable expressions like this one here, we can just integrate it for you and remove it as something that the integrator has to handle manually. There's an ongoing GSOC project to add symbolic integration to symbolics.jl, which we really want to leverage here. And for the things that we can't integrate, but we really don't want to have the OD solver handle, we can always use integrating callback from DiffEq callbacks, for example, and just have that have the transformation happen automatically. There's also something that I really like to add is the support for symbolic structs. So essentially just record types in symbolics, where you have a symbolic variable that represents a bunch of values with the fields, and you can just use get property to access those fields and get a new symbolic value that represents that field. But yeah, that's essentially it. Thank you, and I'm open to taking questions.
All right. Thank you so much. Does anyone have any questions? Hands up for questions. All right, Helmut.
Hi, very nice talk. So how is the delay differential equation interface modeling toolkit coming? Are you working on this?
Sorry, the latest version of?
Delayed differential equations?
Yeah, so delayed differential equations, we do support those. They do work. I'm sorry, I didn't quite get like how are they coming along is what you asked. There are some it does work. I mean, and like it's sort of there. There are a few things I guess we'd like.
I think most of the issues I think that you would have had would have been solved with the system unification with the Modeling Toolkit v10. Yeah.
Yeah.
So one of the issues with the delay differential equations before was it kind of sat in the space of like, oh, you don't really have a delay system, so how is it handled? With having one system type, it's basically able to say, okay, I can handle these delays. Oh, if you have stochasticity, this is where stochastic things go. Da, da, da. So stochastic delay differential equations and delay differential equations got pretty much a lot of bugs worked out just through the fact that we simplified out the system behind it.
Right. Yeah. Thank you.
Any other questions? Yes, Sebastian.
You mentioned something about running MTK on the GPU. Can you talk more about that? Like, would it?
Sure. Yeah. So this is still like, just as a disclaimer, this is still a ways off. I mean, we need like array support and then be able to target reactant with our code generation. But reactant is a package that uses LLVM and MLIR to be able to generate really efficient array code, because that's what MLIR is really good at doing. And the idea is that we can generate functions that are really friendly to reactant, have reactant take that, trace through the function, and generate the optimized MLIR, and then have that MLIR be compiled to a GPU kernel or to something that can run on TPUs, for example, or and stuff like that. So ideally, as transparent as possible, is generate the code, ask reactant to do something on it, and solve the problem.
Yeah, I will say that Modeling Toolkit code for ODEs does generate on GPUs. I think I made that the documentation for that last week or so actually go live on the latest stable version of diffeq GPU. Modeling Toolkit with the differential algebraic equations currently does not build for GPUs for the kernel methods, because the kernel methods need to have support for the initialization process, and that currently is not GPU compatible. I have a Claude agent trying it out though, so we'll see if it ends up being done by the end of JuliaCon. Any other questions? Any? All right, we got a question right here.
So how large of a system would you sort of think is reasonable to model with Modeling Toolkit? So is it 1,000 ODs, 10,000 ODs? What's like, how should we think about it? And is there any advantage of using Modeling Toolkit for extremely large ODs?
Great. Yeah, thank you for that. The definition of a large system is continuously changing, and of course, the goal with all of the symbolic stuff is to make large systems smaller. So I think right now, off the top of my head, I would say that if you're getting to a couple thousand equations, that's sort of when you're really hitting the limits of Modeling Toolkit and hitting those structural simplification runtime issues. That said, one of the really big advantages of using Modeling Toolkit is that it is common sub-expression elimination for these kind of large systems, where suppose you have like a system with like 1,000 equations. Usually, if you simplify them and you remove the aliased variables and like analytically solve for some of the subset of variables, I have seen systems like the Xteam system from the from Bow and Stock, which it turns like around 100, 1,200 equations into 100, 1,200 equations into something like 300 or some that the integrator actually has to handle. And the generated code for that is gonna reuse all of the common sub expressions. So you don't have to generate some like actually manually write all of this kind of messy stuff where you're not computing x squared twice, or you're not computing if else x is less than 3 x squared plus 2y plus z multiple times. It's just gonna generate that for you. And as he showed in his talk, it's an easy 100x speed up for that sort of code gen, just without having to do anything.
Yeah. Well, and so there's a few things to mention. I think that with what you were just saying right there, we should meet with Bowen. I just realized that there's probably an algorithm that we can have to be able to make it so that way they can regenerate loops. So let's talk about this at lunch. But the other thing is that the semi-linear ODE problem, I think that that's one thing that's kind of a bit understated right now. So what we see when people say like, oh, I have this gigantic system and it's very difficult for Modeling Toolkit to compile, right? The reason is because it treats everything as nonlinear. But the majority of your equations are actually just linear or quadratic, right? So one of the things that we're doing with semi-linear ODE problem is that we're pulling out the linear part and the quadratic part to say this is just a matrix, this is just a matrix, and so those parts are handled O of 1, right? And so then it really, when we start to say, so we're saying like, oh, currently Modeling Toolkit, Modeling Toolkit before started to choke at about 1,000 equations. Now with hash consing, it's starting to choke about 5,000 equations, right? But now we're changing the definition. We say, oh, 5,000 nonlinear terms of equations. Any equations that you just have linear terms, they don't count anymore, and any quadratic terms, they don't count anymore. So something like BCR or these a lot of these chemical reaction systems, the vast majority of is mass action terms. Mass action terms no longer count in what we count, right? And so there's kind of this like this when we're saying like it's always going to be a statement of what is the current limit of Modeling Toolkit, but I think that one of the key things to kind of note out is that we're trying to find these special forms, especially linear, quadratic, stencils, so all these things that cover PDE operators, so that way they can be handled in a specific way, and they count as O of 1. If we handle those as O of 1, you can still write down a whole bunch of, nonlinear terms like, x to the 2.5 power, like, okay, that doesn't fall, but you can do 1,000 of those and you're okay. Is that fine, right? So we're starting to we're continually trying to find what are the repeated common patterns and specializing on those, and that seems to be the most helpful approach to the scaling of a problem.
Just to quickly add on to that, I think a couple of versions ago, we have a simplification path that actually improves runtimes by a lot. And it was based off an observation that a lot of times people add variables to their model just because they want to be able to observe those variables. So you might want to, maybe for your model, something like x squared plus y is a term that you'd really like to observe. So you create z is equal to x squared plus y. And you don't use z in your equations anywhere. So there's no reason it should actually go through the simplification process. And we're able to just take out all of those equations early and reduce the number of equations that we actually operate on, which actually has a huge impact on the performance.
All right, so we're coming up on time. So thank Aayush for his great talk.
Thank you.
And next up, we will have Dr. Chris Rakakis. I think I've met him before.